Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the longest match in tennis history. We're going to use probability and statistics to try to understand why that match was so long and why it was so much longer than any of the other matches. Let's get to it. So we're going to talk about the longest tennis match in history, and first we're just going to review how tennis matches work. So a tennis match is divided into sets, which are in turn divided into games, which are in turn divided into points. So in order to win a game, you have to win at least 4 points, and you have to lead by 2. You have to have at least 2 points more than your rival. Once you start accumulating games, you have to win at least 6 games and 2 games more than your opponent in order to win a set. An exception to this are tie breaks, which occur when both players have 6 games, and then if there's a tie break in that set, then there's just 1 additional game, and then the set is finished. Whoever wins that additional game wins the set. This is going to be more important. This is going to be quite important for our analysis, and we'll talk about it later. In Grand Slams, which are the most important tournaments, such as Wimbledon, the first player to win 3 sets wins the match. In minor tournaments, usually you just need to win 2 sets. So for example, in the Wimbledon 2023 final, which I really enjoyed because Alcaraz beat Djokovic, the score was the following. In the first set, Djokovic won 6-1. The second one, Alcaraz won 7-6. And you can see that here there was a tiebreak. Then Alcaraz won 6-1. Then Djokovic won 3-6. And finally, Alcaraz won the last set 6-4, then he had 3 sets and he won the match. Alright, so today we're interested in long tennis matches, so let's take a look at some of the longest matches that occurred before 2010, just to get some context. So there was a match which was a doubles match between Smith Van Dillen and Cornejo Filol, I'm probably completely mispronouncing that, which had one of the sets had more than 70 games. There was another match where one of the sets had 46 games. Another one, again a doubles match, had a set that had again 46 games, funnily enough. And finally there was this one that had 60 games. So here you can see that it was quite rare, but there were matches that had around 60, 70 or 40, 60, 70 games in a set. And then came Wimbledon 2010, first round between Nicolas Mahut from France, this guy, and John Isner from the US, from the United States, that guy, he's very tall. So in the first set, they ended up 6-4. Isner won that set. The second one was 6-3 for Mahut. Then the 2 next ones were tie breaks, 1 for each. And then in the final set, back then, Wimbledon didn't have tie breaks. So they had to continue playing until one of the players would win by 2 games. And it was John Isner who won. So finally he won the game by 3-2. But what's remarkable is that that last set ended up 70-68 for Isner. So that last set had 138 games. It lasted more than 8 hours. And when I saw this back then, I was really shocked because I didn't think such a thing could be possible. So today we're going to use probability and statistics to try to understand how is it possible that such a long set happened and why it had never happened before, in the sense that the previous longest set that I could find was 76 games, which is almost half. Okay, so in order to understand why this happened, we'd have to talk a little bit more about some of the details in tennis matches. So it turns out that within each game, it's always the same player who starts the point, which is called serving. And when you serve, you have a strong advantage over the other player who we say returns, because you're serving the ball, the other player returns the ball. Here you can see Rafa Nadal serving. We'll make this more precise in a moment, to what extent this is an advantage. So in our match of interest, it turns out that out of the total of 183 games, the player that was serving won 180 of them. So there was one instance in the first set where the serving player didn't win the game, another one in the second set, and then there wasn't another one until the very end of the fifth set. So overwhelmingly, the player that was serving won the game. Each of the games, I mean. So an explanation for why the tennis match was so long is that both players served extremely well, but also returned pretty badly. And because of that, they were taking turns winning their serves for many games, and that's why the match lasted so long. So this is quite obvious to anyone that knows anything about tennis, but we're going to make it a little bit more precise. So how can we make this precise? Well, we can try to compute the probability of something like this happening. The probability that a set has 138 or more games. We're going to focus just in the last set. The other sets were not anything extraordinary. So we're going to make some reasonable assumptions and try to compute this probability. Why? Because then once we have this probability, we can see if it's a high probability, then we'll be like, well, this actually was quite likely under the circumstances. If it's a super low probability, then we have not really explained why that could happen. It's not obvious how to estimate this probability, but let's see how we can go about it. It's going to be very helpful to first estimate the probability that each of the players wins a point. So this in tennis, this is usually called the point win percentage. This is the fraction of points that we can expect a player to win. Let's take a look at the point win percentage for different players, just to get some context for this. So as I said, it's very different for a player to serve or to return. As an example, let's take a look at Novak Djokovic, which is arguably the best tennis player in tennis history, definitely the one with the most accolades. So over his whole career, his serve point win percentage is 68. Pretty high. So he wins 68% of the points where he's serving. What about when he's returning? Interestingly, he only wins 42% of the points when he's returning. Here you can see, like, this is probably the best tennis player in tennis history, and he still wins less than half of the points when he's returning. So you can see that the player who is serving really has a strong advantage. Now let's take a look at a current player who is in the top 10, Alex de Minaur. His serve point win percentage is 64, his return point percentage is 40. So here you can see that the margins between players are relatively small, right? So Djokovic, the best player in tennis history, de Minaur is a good player, top 10, but nothing extraordinary. And the gap is relatively small, so 4% for serve and just 2% for return. Holger Rune is in the top 20. He serves slightly better than de Minaur and returns a little bit worse, so 65%, 37%. And finally, just to give you a little bit more context, so Munar is in the top 30 or top 40. His serve win percentage is 61, his return win percentage is 39. So now that we have this context, let's take a look at the serve point win percentages for our two players that we're interested in today, John Isner and Nicolas Mahut. So John Isner was he's already retired. So he served incredibly well. His serve point win percentage is 72. So 4 percentages more than Djokovic, for example. But he returned pretty badly, with all my respects to John Isner, who was a fantastic player. So if you see here, like, Rune is not a great returner. Isner has 7% less point win percentage than, for example, Rune. Now let's take a look at Nicolas Mahut. Nicolas Mahut was a strong server. He has a 64 point win percentage with his serve, not as good as Isner. Isner was really incredible. And his return point percentage is actually relatively low, 34%. So in our match that we're interested in, a really extraordinary server and weak returner was playing against a strong server and weak returner. So you can imagine that when they play each other, they're serving against a weak returner and they're returning against a really good server. So you can see that this could get compounded, and their point win percentage when they play each other could be higher for the serve and lower for the return compared to their usual ones. And in fact, that's what we observe. If we just look at our match and we see the fraction of points that Isner won with his serve, it was 76.2%. So it goes up to 76.2%, which is really high. And his point win percentage with his return, the fraction of return points that he won, is just 21.3%, super low. And the same thing happened with Mahut, 78.7% with his serve. So he won an overwhelming majority of the points where he was serving, and just 23.8% on his return. So he was returning also pretty badly. So now the challenge is that we have estimated these point win percentages for our match. We have determined that the probability that Isner wins a serve point is 76.2%, and the probability that Mahut wins a serve point is 78.7%. But how do we translate this to the probability that the last set was so long, to the probability that the last set lasted 138 or more games under reasonable assumptions? Let's try. So if you have taken any probability and statistics classes, you may have seen problems like this where they give you some probabilities and then you have to derive some related probabilities, and we could go about it in that way. So here, reasonable assumptions are that the points are independent and that they're identically distributed. So each player, when they're serving, has the same probability, always the same probability of winning the point, and the points are independent. Of course, you might be wondering, are these assumptions completely true? They are not, but when we're doing probabilistic modeling, we always have to make assumptions, otherwise it is intractable to compute anything. And for tennis, these are not bad assumptions, because after each point, they stop and they reset. So one could think that this independence assumption is quite reasonable. Same with the identically distributed assumption. The fact that they have the same probability of winning each point is not bad, but it doesn't take into account certain things like fatigue or pressure when it's a very important point. That is true. But anyways, we're going to make these assumptions. And now we want the probability of the game lasting the set lasting. I'm sure I'm confusing set, points, and games. Hopefully, you can get it from context when I make a mistake. But basically, the probability that the set lasts 138 games or more is equal to the probability that it lasts 138, 139, and so on and so forth. Okay, because these are disjoint events. Now let's just focus on one of them. If we want the probability that the set lasts exactly 138 games, we have to compute the probability that Isner first. So we're going to look at sequences of length 138. For example, maybe Isner wins the first one, Mahut the second one, then Isner the third one, and so on, and they alternate, perhaps, until at the end Mahut maybe wins two of them. That's one specific sequence. For that sequence, if we assume that the games are independent, then we can just multiply the probability that each of them wins each of the games in the sequence, and multiplying them together, that gives us the probability of that exact sequence of 138 games. But now we have to add the probability of the rest of possible sequences, so we have to see every possible sequence that goes up to 138 games. We will also have to do that for 139, 140, 141, so you can see that it is getting extremely complicated. But here I'm assuming that I've computed the probability that Isner wins a game and Mahut wins a game. How do we do that? Well, that's where we exploit the fact that we have estimated the probability that they win each point. So if we want the probability that Isner wins, for example, the first game, now we have to see what happens in each point. So First, we have this sequence of points where Isner wins just 4 points and that's it. That's the game. That's one way he can win the first game, but there's several other ways, right? He can win the first point, then Mahut wins the second point, and then Isner wins the 3 next points. So now we have to look at all the possible ways in which Isner can win the game and add their probabilities together, and notice that we're assuming that the probability of each point is independent. So here is where we would put in the probability that he wins if he's serving. If we assume that he's serving in the first game, the probability his serve point percentage times his serve point percentage again, and so on. And here, if he's returning, we would put the return, 1 minus the probability that Isner wins, or the return point percentage for Mahut, which are the same in this case. Maybe I made that a little bit too complicated. The point is that in order to compute the probability that Isner wins the game, we have to look at all the possible sequences that lead to him winning the game, and there's quite a few of them. So we'd have to do that and then plug it in here, and then look at all the possible games, like all the possible number of games, 138, 139. So this is in principle not impossible, but it would get extremely complicated. And I'm not entirely sure it's not impossible because I haven't really kind of worked through it. But we actually in practice never do this, even though from your homeworks in your classes you might imagine that this is how we go about computing probabilities. In reality, there's a much easier way and an often much more tractable way of computing these types of probabilities, which is through computer simulations. So simulating this is actually pretty easy, and I have a link to the code in the description of the video so you can take a look. So here is Python code. Even if you're not familiar with Python, I'm just going to walk you through, so don't worry. This is code to simulate a game. We're going to simulate a game given that we know the win percentage when a player is serving. Okay, so what we do is we initialize the points for each player, the player who is serving and the player who is returning, to 0. And now we have this loop that continues while the game is happening, each point is happening, and it continues while both players have less than 4 points. Then we're sure that the game should continue, and while the difference between the two players is less than 2, because even if the players have more than 4 points, or one of them has more than 4 points, 4 points or more, I mean, if their difference is less than 2, then the game needs to continue. Okay, and what happens in each point? Well, we randomly generate a number between 0 and 1, and if that number is below this win probability, the probability of winning a serving point, this, I'm getting confused, serve point win percentage, then we say that the serving player won that point. So just to make this clear, imagine that this number is 0.9, then this guy here is going to be smaller than 0.5 90% of the time, because it's uniformly distributed between 0 and 1. That's what that function from Python does. So 90% of the time, the serving player is going to win the point, which is what it should be, because we're assuming that the probability of him winning the point is 0.9. Otherwise, the returning player has won that point, so we give the point to the returning player. Now the loop continues until it's done, and when it's done, we check what player won more points. If it's the serving player, we say that the serving player won, and if it's the returning player, we say that the returning player won. So very simple. And again, you can take a look at the Python script and run it and play around with it. Now this simulates a game. We also need to simulate a set, but if we can simulate games, it's quite easy to simulate sets. So to simulate the set, we need the probability. So this is the function that simulates a set. We need the probability of one player winning their serve and the probability of the other player winning their serve. We initialize the games for each player to 0. We decide what player starts serving. So here we set the serving player to be the first one, but then with probability 1/2, again with this trick where 50% of the time this guy is smaller than 0.5, we switch and we let the second player start serving. And now we have another loop, which is over games instead of over points. And this loop ends this loop continues as long as the players have less than 6 games, or if one of the players has more than 6 games but the difference is less than 2, then it still continues. And now if the first player is serving, then we use their win probability serve to the probability of them winning their serve to plug into the simulated game, and we check whether they won. If they won, we add a game to their tally, and if not, we add a game to the tally of the player who is of the second player because they're returning. And now, of course, we have to switch. Now the second player is going to serve. If the second player is serving, then we use their probability of winning their serve. And if simulate game returns a 1, that means that the serving player has won. So in this case, that's player number 2. We add a game to their tally. And if not, we add a game to the tally of player 1. And then we have to switch again. Now player 1 is serving, and we continue in this loop until the set is finished. And then we return the number of games that each of the players won. Why? Because we want to sum them up to see how long the set was. Okay, so as you can see, computing by hand the probability of a player winning a game or winning a set, or the game being longer than 138, the set being longer than 138 games is actually really, really complicated, but simulating it is quite easy. Okay? And now, what do we do with these simulations where we're going to exploit the intuitive definition of probability? Remember that the probability of an event, we can imagine it as the number of times that event would occur if we were able to repeat things over and over. So probability of someone winning an election would repeat that election many, many times. And if the probability is 70%, that means that when we repeat the election many, many times, that person wins the election 70% of the time. This can be exploited through the Monte Carlo method if we are able to simulate this phenomenon that we're interested in. In our case, if we're able to simulate matches, the way the Monte Carlo method works is you generate a lot of simulations. In our case, it's going to be 1,000,000 simulations. And then you check if your event of interest happened, how many times your event of interest happened, and the fraction of times it happened over this very, very large number of simulations is the probability of that event. In our case, we're interested to see what is the probability that a set lasts 138 games or more. We're going to simulate many sets, and then we're going to see what fraction of those sets has a number of games that is equal to 138 or more. Because of the law of large numbers, if we have enough simulations, then we are guaranteed that the estimated probability is going to converge to a true probability. And because we're simulating on a computer, we can afford to do a lot of simulations. So this is usually not going to be a problem. So this is 1,000,000 simulations. This is a histogram with the number of games that occurred in each of these sets. So we're simulating 1,000,000 sets between Mahut and Isner, and then we're counting how many times the set had 50 games, how many times it had 100 games, and so on. We're actually interested in this tail over here because we're interested in what's the probability that there were 138 games or more, like in the match that we actually observed. So we're going to need a logarithmic scale on the y-axis in order to actually see what's going on. And when we put that logarithmic scale, we realize that there's a fair number of games that have that duration. In fact, almost 1% of the games have that duration. If you're nervous about what's happening here is that over the million simulations, the probability of there being like 350 games or more is approaching 1 divided by 1 million. So that's why we don't see it that much. But this is not problematic because we're mostly interested in these guys here, which are many more. So this is happening like 1,000 times or more within our simulations. So we're not worried. Like this is contributing, this tail here, which is inaccurate because we only have 1 million simulations, is barely contributing to our probability estimate. Okay, that's a little bit technical, not too important. Essentially, from this, we can see that we have enough simulations that, approximately 1% of the simulations end up in 138 games or more, which, is low, but it's not crazy. Things that happen 1% of the time will happen, 1 out of 100 sets between such players, you would expect this to occur. So as a side note, now we're interested in estimating the probability that the set is super long, but you can actually use these simulations to also predict who is going to win the match. How would you do that? Well, you would predict the match. So instead of predicting just one set, you would predict up to however sets are necessary for one of the two players to win, and then you would repeat that over and over and over, and you would see what percentage of the time each player wins. So if we do that for our match, it turns out that Isner has a probability of winning which is 38.7%. He actually ended up winning. This just shows that the two players were quite evenly matched. You might think, oh great, so then it's super easy to predict tennis matches. Well, the catch is that you need to estimate the point win percentage before the match happens. Now we're lucky, right? Because we're just analyzing the match after it happens, so we have access to the point win percentage for each of the players. Of course, it's not the truth, right? It's just the observed one. But still, if you wanted to predict who wins a match, you have to determine the point win percentage for each of the players when they play each other under those conditions before the match, which is probably quite complicated. And there you would have to take into account the profile of each player, what happens when they play each other, the surface, the weather that day, etc. So it's not so easy, but this gives you a way of translating these point win probabilities, which are more intuitive to estimate, and translate them to the probability that one of the two players wins the match. All right, that was just a side note. Let's go back to our problem of talking about why this long set happened. So we have these estimated serve point win probabilities, which are 76.2% for Isner and 78.7% for Mahut, but do we trust them? Because we're computing them from a finite amount of data. Well, this depends on the sample size, right? If we're observing a small number of points, then these estimates will probably be very noisy. If we're observing more points, then they will be less noisy. To make that precise, we can look at 0.95 confidence intervals to quantify the uncertainty, and you can look at how these guys are computed for probability and proportions in the video that I have about that or in the book. So assuming the points are independent, what we're assuming anyways all over the place, then the confidence interval for Isner is between around 72% and 81% roughly, and for Mahut it's between 74 and 83%. Okay, so roughly between around 75 going up to 83 for Mahut, going up to like around 81 for Isner. So now let's see how different serve point win percentages translate to a probability of observing a really long set. So up to now, well, before we did it just for the just assuming that each of the players had that exact serve point win percentage, but now I'm interested in seeing what happens if the serve point win percentages are not exactly those. So in order to kind of look at it cleanly, first we're going to assume that both players have the same serve point win percentage, and then we're going to look at what happens if they're different. So if they have the same point win percentage, here I'm showing the serve point win percentage in the horizontal axis. We see something very interesting. In the vertical axis, we see the probability that a set lasts 138 games or more. So for the typical serve point win percentage that you would see in normal players, which are always, typically below 70, definitely not going beyond 75, that probability, which we see here, is actually very, very low, like 10 to the minus 4, 10 to the minus 5. So it would be extremely, extremely rare to see such a long set. But here, in our particular match, we saw that because two very strong servers and weak returners were playing each other, their serve point win percentage was going beyond 75. And when that happens is when we start seeing probabilities that go close to 1%. So now it's not so crazy that you would observe this. And then if the serve point probability goes beyond that, it actually becomes very likely. Basically, the two players are just kind of winning their serve all the time. So the set lasts for very, very long. And what's interesting is that usually normal tennis matches are in this regime, but then there's this phase transition which we are observing in this match when the two players have a very high serve point win percentage. Now let's take a look at what happens when the players have different serve point win percentages. If we fix the serve point win percentage of one player to be 70% and we vary the serve point win percentage of the other player, realize that because the sets are only long when you alternate between serves, this probability just goes up and up and up as a function of the probability or the serve point win percentage of the second player. Okay, which is kind of interesting. Perhaps to be expected, but kind of interesting. So I've shown you this for 70%, this is what happens for 75%, and this is what happens for 80%. So again, if the players are below 75%, which happens here and here, okay, I guess I'm making that a little bit ugly, so it happens here, then the probabilities are very low. The probabilities are 10 to the minus 3 or less. Now, as the players have a serve point win percentage of 75% or above, as was the case in our match, then maybe I'll use another color. Then the probability is, like approaching 1%, and eventually, maybe, let's see, up to 80, so more here. I guess we are here in our match of interest. And if we go beyond that, then the probability is actually pretty high. But again, in our case, these two strong servers, weak returners are in this regime. So again, we see that the probabilities are around 1% for our match of interest. So now we're going to explore the question of why was this observed just once. Presumably there are other players that serve very well and return pretty badly, but this game was quite extraordinary. It had almost double. This match was extraordinary. The last set had almost double the games of any other match in history. Well, our strategy to try to answer this question using statistics is basically to ask ourselves how many similar matchups between what tennis aficionados usually call serve bots, so players that serve extremely well and don't return too well, how many of those matchups happened before 2010. And then we can compute the probability of more of a set lasting 138 games or more exactly once, given that there were that many similar matchups. So in order to find the number of matchups, we identify strong servers and weak returners that are sometimes called serve bots, as I said, and we see how many times they played each other. So I use ChatGPT for this, and you let me know in the comments if ChatGPT missed anything. But to me it makes sense, because when I was following tennis, I remember Ivanisevic, I definitely remember Rusetsky and Krajicek, Mark Rosset also, Filipoussis, Karlovic, and it makes sense to me that one would classify these players as strong servers, weak returners. Notice that we have two familiar names here that ChatGPT found, which are Nicolas Mahut and John Isner, so our two players of interest, are classified in this way, which is reassuring. Now there's a catch here, because most of the tournaments that players played before, after the 70s, had this tie-break rule where if a set reached 6-6, then the players would just play a decisive game called a tie-break that would end the set. So then the sets could not go on and on. This was quite widespread since the 1970s, as I just said, except for the final deciding set in certain tournaments, including Wimbledon, which is why our longest, this super long match actually was able to happen. And after that, Wimbledon actually changed it. So it is no longer possible. Maybe partly motivated by this super long match. So this has been a very important reason why there haven't been more very long sets, because when we asked ChatGPT how many sets without tiebreaks occurred between these players, according to ChatGPT, it was just 20 sets. So it's a relatively small number. This is probably underestimating the number of sets because, first of all, maybe not all of servots are in our list, and also we're ignoring doubles. But anyways, we're going to make this assumption that we're focusing on on games between single players, and that sounded a bit strange. Non-double games, singles. We're focusing on singles, and we're going to accept that it was 20 sets. So now we want to see the probability of observing 138 games in a set or more only exactly once, given all the assumptions we've made. And if that probability is relatively high, then we're going to be like, okay, under all our assumptions, it was quite reasonable that we would observe such a long match, such a long set, and that we would observe it only once. If it's super low, then we haven't really explained anything. So to make the notation a bit clean, imagine that the probability in a single set of having 138 games or more is theta. And realize that for our circumstances, theta is going to be roughly 1%, maybe a bit, depending on our assumptions, maybe a bit less, maybe a bit more. So now the probability of observing it just once in 20 sets, for this to happen, we have to take into account the different sequences of 20 sets in which this can happen. So basically, one of those sets is going to be super long, and then the other ones are not going to be as long. It could be the first one, it could be the second one, it could be any of the 20 ones. So there's 20 such sequences, and under the assumption that the games are independent, each of the sequences has the same probability. So theta for the set that was actually long, and 1 minus theta for the remaining 19 sets that were not so long. When you compute that, for many possible values of the probability of observing 138 games or more in a set, so this is theta, this is the probability that we're interested in, observing it just once in these 20 sets, then we see that if theta is small, if the probability of a long set is small, then we never see it in these 20 sets. If it's very high, then we never see it only once. What's happening there on the right is that we see it multiple times because it's so likely. But we are exactly in the middle, around 1%, and around 1%, the probability here, you can see, is roughly, maybe I'll say here, is roughly between, I'm going to say 7% and almost 30%. So, it's relatively likely. So under our assumptions, it seems that it's not so unlikely that we would have observed such a long set and that we would have observed it just once. Here, so that you can visualize all of our results, basically, Mahut had a serve point win percentage in the match that we're interested in that was between 75 and 84. So here, more or less. Okay, and Isner had a serve point win percentage that was between 72 and 80. So that would be this. And we can see that if we look at the at our vertical axis, that translates to a probability that goes, maybe I went a bit too low, like roughly like this, right? So it's around 1%, could go lower than 1%, could go almost up to 10%. And when we look at how that translates, that's for a single set, right? When we look at how that translates, sorry about that, to the probability of observing that just once in 20 sets, then we're essentially between here and here. So we're between 5% and around 25%. Okay, so it's actually really not that unlikely under all the assumptions we have made that we would observe such a long set and that we would observe it only once. Okay, so the conclusion here is that under our assumptions, a match with 138 or more games occurs with non-negligible probability if both players are strong servers and weak returners. So we need for the point win, the win percentage for the serving points to be 75% or above, which is not crazy for such strong servers and weak returners as Isner and Mahut. And then, given that the number of sets without tiebreaks was quite reduced, we have determined that it was around 20 between such players, but probably there were some more. Then the probability of observing just one game like that is actually quite plausible. It was between 5 and 25%. This, of course, under our assumptions, where the points are independent and identically distributed, which, for example, ignores fatigue, which for such long sets is probably a very important factor. And that's all I got. Hopefully, you're satisfied with the explanation of why the longest tennis match in history happened and why it was so much longer than any other match. Thank you very much.